Hello dear students, welcome to Learning Chemistry is Easy and Fun. We are continuing with our topic Structure of Atom. Today's lesson is lesson number 8, where we shall be talking about the Bohr-Rutherford model of the atom, which popularly you know as the Bohr model of the atom. Now why are we calling it as the Bohr-Rutherford model of the atom? Because Bohr picked up a few suggestions from the Rutherford's model of the atom and modified them in order to incorporate the Planck's quantum theory and based his model of the atom on this theory of Planck's known as the Planck's quantum theory. Now, if you are not very clear about the Planck's quantum theory, I would suggest that you go back to lesson number 6 and 7 in this series of videos, so as to be fully clear, because otherwise you will find it difficult to correlate to what we are going to talk about today. Now, as I said, Bohr picked up a few points from Rutherford's model and improvised upon them in order to explain or in order to overcome the drawbacks which were there in the Rutherford's model of the atom. The first point of the Bohr's theory is the nucleus, similar to what Rutherford had suggested. Now, according to Bohr as well, nucleus is the central part of an atom. This nucleus is very small compared to the actual size of the atom, as we had seen in the gold foil experiment by Rutherford. It is heavy because it contains all the positively charged particles which are in an atom, and those are the protons. And it is the central part of the atom. So we can say, if you have to write it as a point, I have broken it down into subpoints so that it's easier to remember as well. So an atom consists of a central, small, heavy, positively charged nucleus which contains the protons. Coming to the second point, this is where Bohr had to improvise on Rutherford's model. Now, Rutherford had said that the electrons are moving around the nucleus just like the planets around the sun. So, we had named it as the planetary model of the atom. Bohr said, yes, agreed. The electrons are moving around the nucleus, but they are not moving around randomly, and he suggested they are moving in circular paths which are very well defined. When we say well defined, means that he gave them values. He said that these are circular paths. Now these are not circular paths that you can see, but these are trajectories or paths, just like you have the orbit of a planet. Again, yes, they are moving around the nucleus, but these are well defined. That means they have a fixed value as well. There is a certain radius of each orbit, and he called them as fixed energy or energy levels or stationary states. The reason for calling them fixed energy, energy levels or stationary states. As the name indicates, if an electron is present in a particular orbit, it is associated with a fixed amount of energy. This is where Bohr had differed from or improvised upon what Rutherford had suggested. So first of all, he called these well-defined circular paths as 1, 2, 3, 4 and so on. So it's the first orbit, second orbit, third orbit, fourth orbit and so on. Alternately, he also named them as K, L, M, N and so on and so forth. So these energy levels that we are talking about are either 1, 2, 3, 4 or K, L, M, N and so forth, and not A, B, C, D. The reason for this, you will try finding it out yourself. As we said, these are fixed energy. An electron in a particular orbit will have a fixed amount of energy associated with it. In other words, if it is in the first orbit, its energy is E1. If it is in the second orbit, its energy is E2. And these energies are increasing as we move away from the nucleus. So the energy of the third level is more than the energy of the second level, which is in turn more than the first energy level, and so on and so forth. So if an electron has to jump from one energy level to another, it has to gain energy. And how much energy it will gain is also fixed. There is a certain value associated with it, and the term that we give here is quantization of energy, giving a specific value, a quantity, a physical quantity or a physical relation to this energy. So the difference of the two energy levels is quantized, and this is called h nu, where h is the Planck's constant, which we have explained earlier in Planck's quantum theory, and nu is the frequency of the emitted or the absorbed radiation. Why absorbed or emitted? If it jumps from a lower energy level to higher energy level, it will absorb energy. On the other hand, if it jumps from higher to a lower energy level, now because a lower energy level means a lower amount of energy associated with it. So whatever excess energy is there, it will emit it out. So there can be absorption or emission of energy depending upon whether the electron has moved from lower energy level to higher energy level or higher energy level to lower energy level. So this is where Bohr added the energy value to each of the orbits of the atom. So this is called quantization of energy, which was very beautifully stated in a sentence saying that electron does not flow. It jumps from one energy level to another. It could be high to low or low to high. Based on this concept, he also gave the amount of energy associated with each orbit. So En is given by minus k square 2 pi square m z square e to the power 4 upon n square h square, where the meaning of the symbols are, we have pi, of course, the constant 3.14, mass of the electron is m, z is the atomic number, e is the charge of the electron, k is called as the permittivity of the medium. Now k is taken into account because we are talking about this energy in the SI system. Now all of this boils down to a simple expression, minus 2.178 into 10 to the power minus 18 upon n square joule per atom, when I am talking for an atom like hydrogen whose atomic number is simply taken as 1. We are limiting our study to hydrogen because we do not want to complicate the things right now. So I am giving you simple expressions. The derivations of this will be taken up in the next video. If you are talking about the energy in joule per mole, we have minus 1.312 into 10 to the power 6 upon n square. Why? Because we will convert per atom into per mole by considering the Avogadro number 6.023 into 10 to the power 23. 1 mole is an Avogadro number of atoms. These electrons, the last point, are moving around the nucleus. They are not associated inside, which is very much of what Rutherford had suggested in his model. Coming to, as I stated earlier, these are well-defined circular paths. So there is a value associated with these circular paths. Rn, that is the radius of an orbit, is given by n square h square upon 4 pi square m z e square k. K again permittivity, E charge of the electron, Z the atomic number, m the mass of the electron, 4 pi square, n is the number of the orbit. So if you're talking on the first orbit, second orbit, third orbit. Now understand over here, the electron cannot be in between. It can't occupy a space in between the first and the second orbit. This n is always a whole number. So what we have here is n can be 1, 2, 3, 4 and so on. It can never be 1.5, 2.5, 2 3/4. It can never be like that. You can never have decimal values for this, and it's a whole number. Now this expression, when valid only for hydrogenic atoms, that means atoms which are similar to hydrogen having only one electron in them. So we will, if we put down the value 6.6 into 10 to the power minus 34, 3.14, mass of the electron and all the other values, this simply boils down to a simple expression, Rn is equals to 0.529 upon Z into n square angstrom units. 1 angstrom units is 10 to the power minus 10 meters. It's a unit of length. Now, so that means we have the radius is a fixed value. Now, if the same expression is used in order to find out the radius of the first orbit, Rn will take the value of 1. So my expression comes to 0.529 upon again 1. So this is 0.529 angstrom units. So the radius of the first orbit of hydrogen atom, which is the simplest and the lightest element known to us, is 0.529 angstrom units, and this is called as Bohr's radius after the name of Bohr, who gave us this concept. Yes, I am giving a pause so that you can absorb these points. If you are still confused, please pause the video, go through the points. They are listed on the board. Any confusion, please message me through the comments section. Coming to the last point in Bohr's theory, quantization of angular momentum. Quantization. What do you mean by quantization? Giving a quantity, giving a value. Just like we have quantized energy over here, similarly Bohr quantized the angular momentum. What is angular momentum? Let's break it down. Linear momentum. I am moving in a specified direction on a straight line path. I have what is called as linear momentum, denoted by P. What is linear momentum? The product of mass and velocity, mv. Angular momentum. Now I start going around in a circular path. Now again there is acceleration because my direction is changing. There is momentum. Angular momentum is nothing but the product of linear momentum. So this is my direction and this is the radius of the circular path. Angular momentum is linear momentum into the radius. So mvr. He said that angular momentum of this electron, which is going around on this circular orbit, is an integral multiple of h upon 2 pi, where n, as I said in the statement itself, it's an integral multiple. Your n can have 1, 2, 3, 4 and so on values. It can never be a decimal or a fraction. So mvr is equals to nh upon 2 pi. Here we have listed the major points of Bohr-Rutherford model of the atom, or what is popularly called as the Bohr's model of the atom. We shall be deriving the expressions in case you want. We shall be deriving these expressions in the videos to follow. But I am not dealing with them over here because not everybody is keen to know the derivation. Depending upon the kind of preparation you want and depending upon your focus areas, I think for you, Bohr model of the atom, this should be sufficient. Any doubts? Don't hesitate to ask. If you liked the video, please don't forget to subscribe and share it with your friends, because knowledge is best enhanced when shared. Happy studying to all of you. See you in the next video.